Hello and welcome back to Engineers Olympiad, where learning meets success. This is the video lecture number 4 of the chapter Theory of Errors in Surveying. We have completed 3 video lectures and this is the 4th one. They're already up on the channel Engineers Olympiad. You can watch those videos before watching this video. So let's begin. Relative precision. What is precision? As already discussed in the previous video lecture, precision of a measurement denotes its closeness to the another measurement of the same quantity. All right, so if a quantity is measured several times and the values obtained are very close to one another, we will say that the precision of that measured value is quite high. And now today's topic, what is this relative precision? Relative precision, or the degree of precision, is used to express the precision of the various measurements, and it's usually expressed as a ratio between standard deviation and mean value of the measurement. All right, so relative precision is a ratio between standard deviation and the mean value of that quantity. So I may write it down. Relative precision is equal to sigma by m, where sigma is the standard deviation and m is the mean value of that quantity. And it's usually expressed with numerator as unity. So I may write it down as all right, and the denominator is generally rounded off. Let's take an example and calculate relative precision. If the standard deviation is plus minus 0.03 meters, all right, and for the mean value of the length of the line 615.41 meters, all right, if the standard deviation is plus minus 0.03 meters, for the mean value of the length of the line 615.41 meters, our relative precision will be, it's a ratio between standard deviation and the mean value of the quantity. And as already discussed, it is taken with the numerator as unity. So by calculations, it will come equivalent to how much? 20513.7. And as already discussed, we take numerator as unity. So my relative precision for this particular set of measurements, whose standard deviation came out this, and the mean value of the length of the line was this, came up equivalent to this, and the denominator is rounded off. So let's suppose approximately the relative precision is 1 by 20500. All right, so this was about relative precision, which is a ratio between standard deviation and the mean value of the measurement or a quantity. All right, moving on. Let's study about discrepancy. What is discrepancy? A discrepancy is a difference between two measured values of the same quantity. Difference between two measured values of the same quantity is known as discrepancy. All right. And this must be noted that if discrepancy is small, it indicates that the mistakes and random errors are also small. If our discrepancy is small, it definitely means that our mistakes and our random errors, also known as accidental errors or compensating errors, are also small. but it does not guarantee that our systematic errors will also be small. All right? It does not guarantee that they will also be small if our discrepancy is small. Why? Because each measured value will have large equal systematic errors which have not been corrected and no corrections have been applied to them. All right? So if our discrepancy is small, it definitely means that mistakes and random errors or accidental errors are small, but it does not guarantee that our systematic errors will also be small. And the precision is revealed by repeated measurements and by observing discrepancies. All right. So this was about discrepancy. Moving on. We have studied relative precision and we have studied discrepancy. Now let's study degree of accuracy. What is accuracy? Accuracy denotes the closeness of the measured value to the true value. All right. The degree of accuracy, this indicates the accuracy attained in the measurements. What does this indicate? Accuracy obtained or achieved in our measurements. All right. So the degree of accuracy indicates the accuracy which we attain in our measurements, and it's usually expressed as the ratio of the error and the measured quantity. Degree of accuracy it is expressed as the ratio between the error and the measured value of a quantity. All right. For example, a degree of accuracy of, let me write it over here. A degree of accuracy of 1 in 10,000. A degree of accuracy of 1 in 10,000 indicates that there is an error of 1 unit in 10,000 units. All right. So the degree of accuracy indicates the accuracy as attained in our measurements, and it's usually expressed as an error between ratio between error and the measured value of a quantity. All right. So if it's written that degree of accuracy is 1 in 10,000, let's suppose that means there is an error of 1 unit in every 10,000 measured units. All right. And let's see how we take this degree of accuracy in linear measurements. All right. The degree of accuracy of the linear measurements is usually expressed as a ratio of the probable error to the measured distance. Probable error to the measured distance in linear measurements. All right. Degree of accuracy in linear measurements is taken as the ratio between probable error to the measured distance. Let's illustrate it with the help of an example. For example, if there is a probable error of, let's suppose, plus minus 0.05 meters in a measured distance of 584.65 meters, there is a probable error of how much? Plus minus 0.05 meters in a measured distance of 584.65 meters. Our degree of accuracy is ratio between probable error and the measured distance. All right, and we usually express it with numerator being unity. So by calculations, this will be how much? 1 by 11693. And we usually round off the denominator. And let me write it down as 1. All right, so this is my degree of accuracy, and this indicates that there is an error of 1 unit in every 11,700 units. All right, so this was about the degree of accuracy in linear measurements. But these days there is a trend to express degree of accuracy as a ratio of standard error instead of probable error. All right, so these days we use which error? Standard error or standard deviation instead of probable error to calculate our degree of accuracies. All right. So I'll say degree of accuracy is equivalent to standard error by measured distance. For linear measurements. All right, let's see what is the degree of accuracy for a traverse. The degree of accuracy of a traverse is usually expressed as a ratio of the error of closure to the perimeter of the traverse. Degree of accuracy in a traverse will be equal to ratio between error of closure divided by perimeter of that traverse. Total perimeter of the traverse. All right. Let's take an example. For example, if there is an error of closure of 0.1 meter in a traverse and whose perimeter is 200 meters, our degree of accuracy will be how much? 0.1 by 200. All right. So if I'll express it with numerator as unity, it will be equal to 1 by 2000. So the degree of accuracy in a traverse is a ratio between error of closure of traverse divided by the total perimeter of traverse. And in this traverse, whose error of closure was 0.1 meters and whose perimeter was 200 meters, there is a degree of accuracy of 1 in 2000. That means there is every 1 unit of error in 2000 units. All right. Angular measurements. For angular measurements, the degree of accuracy is usually expressed as K under root N. For angular measurements, we express the degree of accuracy as K multiplied by square root of N, where N is the number of measured angles. Number of measured angles. All right. And K, this is a ratio between angular error or closure divided by number of angles measured, square root of that. All right. Angular error divided by square root of number of measured angles. Number of angles measured. All right. So this is the angular measurements and the degree of accuracy. Let's study about leveling. For leveling, the degree of accuracy is usually expressed as K under root of L, where L is the horizontal length of the root. L is horizontal length of the root. All right. And K is error of closure in elevation divided by horizontal length of the root. K, this is the ratio between error of closure in elevation divided by how much? The square root of horizontal length of the root. All right. This was about degree of accuracy in linear measurements, in traverse, angular measurements, and in leveling. The degree of accuracy is the ratio between error and the corresponding measured distance as far as linear measurements are considered. But the trend is to use standard errors instead of probable errors. All right. Now, order of accuracy. We have completed degree of accuracy. Now we'll study about order of accuracy. The minimum degree of accuracy allowed for a particular survey and the range of allowed degrees of accuracy is known as the order of accuracy. What is order of accuracy? The minimum degree of accuracy allowed for a particular survey and the range of the allowed degrees of accuracy. And the most accurate work is designated as the work of the first order accuracy. All right. The most accurate work is designated as the work of first order accuracy, and the work of second order accuracy is less accurate than this one. The work of second order accuracy is less accurate than the work of first order accuracy. Likewise, the work of the third order accuracy and the fourth order accuracy are less accurate than that of the second order accuracy and the third order accuracy respectively. All right. Let's take an example. The following standard of accuracies may be expressed for the horizontal distances for a particular survey. We are taking a particular survey and we have different standard of accuracies for this particular survey, and first order accuracy is equivalent to, say, 1 by 25,000. Second order accuracy say 1 by 10,000, and third order accuracy say 1 by 5,000. So which measurement is more accurate? The first one, whose order of accuracy is 1 by 25,000. How? Because there is an error of 1 unit in every 25,000 units. And in the second one, there is error of 1 unit in every 10,000 units. And in the third one, there is error of 1 unit in every 5,000 units. All right. So this was about order of accuracy, which is the minimum degree of accuracy that is allowed for a particular survey and the range of allowed degrees of accuracy. All right. And that is known as our order of accuracy. Moving on. Accuracy in surveying and the permissible error. As already discussed in the previous video lectures, that it's completely impossible to determine the true value of a quantity, and the true value of a quantity is that value which is free from every type of error. And as already discussed, that some sort of errors always creep in our measurements, our measured distances and our measured angles, so it's quite impossible to determine our true value. Permissible error. What do we mean by permissible error? The permissible error is the maximum allowable limit that a measurement may vary from the true value. True value, or that value which is free from every type of an error, and it's a hypothetical quantity, cannot be determined. But our permissible error is the maximum allowable limit. Maximum allowable limit. All right. Our permissible error is our maximum allowable limit that a measurement may vary from its true value. All right. So the value of the permissible error in any given case depends upon the scale and the purpose of survey. This depends upon the scale and the purpose of survey, and the instruments available, of course. All right. How precise our instruments are. So our permissible error is the maximum allowable limit that a measurement may vary from its true value. All right. The surveyor may be handicapped by rough country, or maybe too short a time, or maybe too small a party, or maybe poor instruments, bad weather, and many other unfavorable conditions. But the limit of error cannot be given once for all. All right. Let me write it down over here. A surveyor may be having many constraints, like he may have to survey in a rough country. There may be bad weather conditions. All right. And he may not be having large manpower, or his instruments may not be that precise. So everything will limit his accuracy and consequently the permissible error. The best surveyor is not he who is extremely accurate in all his work, but he who does it just accurately enough for the purpose of the survey without wasting time or money. All right. So a best surveyor is that surveyor who is extremely accurate in all his work, but he who does it just accurately enough for the purpose of the survey and without compromising on economy, compromising with economy. All right. So he will manage his time, his sources, his money, and accordingly he will make a judgment of how much permissible error he will keep in his measured quantities. All right. Because permissible error is our maximum allowable limit that a measurement can vary from its true value. So it's about the judgment of that particular surveyor who's taking the readings in the field, that he will do it in accordance with the purpose of survey and with managing his resources, his time, his money, and accordingly he will give a good judgment of how much permissible error he may keep in his measured distances. All right. So a surveyor should make the precision of each step in the field work corresponding to the importance of that step. All right. More the step is important, more precisely he will measure that. All right. So this was